Good morning, dear students. Hope you all are safe at home. So we were supposed to start our academic year by this time, but because of COVID-19 lockdown, we were unable to do. So please cooperate with us, listen to the videos or read through the notes which is given to you. These chapters which are done here, no, it won't be repeated in the class. So keep a track of whatever is being done. Okay, so before we start, I want you all to keep your class notes in front of you. We had already started the chapter solid state. That was the first chapter. So let's quickly revise through the topics which are done so far. So I hope you have your notes in front of you. So flip the pages as I go through the topics. I had already asked you all to revise whatever was done. Okay, so we started with classification of solids. So we learned that it's been classified into amorphous and crystalline solids. We learned the differences between amorphous and crystalline solids. Then we moved on to classification of crystalline solids. We learned 4 different types of crystalline solids. Based on the bonding, it was classified into different types. Okay, we learned that. Then we learned what is unit cell, which are the different types of unit cells. BCC, FCC. Yes. Then we calculated the number of atoms per unit cell. The number of atoms in BCC was 2. In FCC it was 4. In primitive cubic cell it was 1. Okay. Then we learned different ways of arrangement of particles. We learned square close packing, hexagonal close packing. Then we learned about the voids. There are two types of voids, octahedral and tetrahedral voids. Then we moved on to a very important portion of solid state, that is derivation of packing efficiency of HCP, BCC and simple cubic. I told you these 3 derivations are very important. It will be asked as a 3 marker. Okay. Next, I think we just did an introduction to calculation of density. Whatever is remaining will be done in the class. Okay. So today we'll start with a new topic. I want you all to take lecture notes as I have not included all the information in the PPT. So you'll have to keep a track of whatever is being explained. Okay. In some cases you might find only pictures. So listen to whatever is being told. Okay. Okay, so we'll start with the topic or defects in solids. So let me explain you what is a defect in a solid. Okay, so if this is a way in which particles are arranged in a solid, one type of defect. Okay, so you can have another type of ion. Okay, if this is NaCl crystal, it can have an ion of K plus inside. Okay, so this is a particular type of defect. Okay, another type of defect. So in this defect, in this defect, you have an extra atom, extra constituent particle. Okay. So this is an error. This is a mistake in this particular crystal. So this is a defect. Okay. Another type of defect. In another type of defect, you can have some deficiency. Okay. See, there is a vacant site here. So this is another kind of defect. So these are certain mistakes in the crystals. Okay, so these are nothing but defects. Okay, so now we'll move on to classification of defects. Okay, so we have point defects and line defects. Okay, defects can be classified into point defect and line defect. So these 2 kind of defects which I explained here are point defects. Okay, defect is around this particular atom. It's around a particular point. So this type of defect is called point defect. Okay. Now, in certain crystal, you can have one full set of particles going wrong. Okay. Those type of defects are known as line defects. Okay. You call it stoichiometric defect. Okay. So under stoichiometric defect, we will learn about vacancy defect first. Okay, so let's see what is vacancy defect. Okay, stoichiometric defect is also called intrinsic defect. So vacancy defect. In this type of defect, some of the lattice sites are vacant. Okay, so here you can see that the crystals are arranged in a particular way, right? It's arranged in a particular way. So you can see a vacant site here. Okay, so this site is said to be vacant. So this is nothing but vacancy defect. So as you can see, there is a vacant space here. Okay, that is why this type of defect is known as vacancy defect. Okay, and this defect can decrease the density of the substance. Okay, so you know that the formula for density is mass by volume. So since there are absence of particles here, mass is going to reduce. Mass will reduce. Okay, so that results in the decrease of density of a substance. Okay, so you just have to know what is vacancy defect and how density is affecting, like whether the density is decreasing or increasing due to vacancy defect. Okay, so next we'll move on to the next type of defect, that is interstitial defect. Okay, in interstitial defect, see, the particles are arranged in columns and rows. Okay, but can you see there are some particles which are not aligned? Okay, some particles are present in between. Okay, so these places are known as interstitial site. Okay, it's so this type of defect is known as interstitial defect. Okay, if it's occupying an interstitial site, so these particles are extra particles. Okay, so this type of defect is known as interstitial defect. So what do you think? How does it affect density? Does the density decrease or increase? In case of vacancy defect, as you have seen, there are particles which are gone missing from the crystal. So in that case, the density decreased. Okay, but here can you see there are extra particles which are added to the interstitial site, right? So since it's added, the density will increase. Okay, so this defect can increase the density of the substance. So this type of defect is known as interstitial defect. This is the second type of defect. Okay, next, the third type of defect is known as Frenkel defect. Okay, Frenkel defect is also known as dislocation defect. Okay, so in this type of defect, what is happening is, see, can you see in this picture, the blue color balls which you can see is a cation. Cations are usually smaller in size. So that's a cation, and the red color balls which you can see is an anion. Okay. So the smaller ion, which is a cation, is dislocated from its normal site to an interstitial site. Okay, so just this is a mistake, just correct it. It's interstitial site. Okay, so here, as you can see, the blue color ion, that is the cation, which was supposed to be here at this place, has dislocated from here to this interstitial site. Okay, so here the cation which was supposed to be at this site has dislocated from this place to an interstitial space. Okay, so now here you can see both the type of defects which you learned earlier. You can see both a vacancy defect and interstitial defect here. Okay, so this, what do you think? This doesn't change the density of the solid. Okay, because the crystal, there is no addition of a new crystal or removal. There is no addition of a particle or removal of a particle. Okay, whatever particle was there here has just dislocated from this place to an interstitial space. So there will be no change in density of the solid. Okay, can you read this fourth point? It creates a vacancy defect at its original site. So in this place, it has created a vacancy defect and an interstitial defect at its new location. At this space, it has created a interstitial defect. Okay, so this defect is also known as dislocation defect because the cation is dislocated from its normal site to interstitial site. Okay, you can learn the examples: zinc sulfide, silver chloride, silver bromide, and silver iodide. These are some of the examples of Frenkel defect or dislocation defect. Okay, next let's move on to the fourth type of defect under stoichiometric defect, that is Schottky defect. Is a vacancy defect. It's similar to vacancy defect, but here, to maintain the electrical neutrality, the number of missing cations and anions will be equal. Okay, so if there are two vacant site of cations, then there will be two vacant site of anions. Otherwise, the electrical neutrality will not be maintained. Okay, and it also decreases the density of the substance. So it's obvious that the density will decrease. Okay, because there are cations and anions which are missing. Okay, so you can see the examples: NaCl, KCl, CSCl, that is cesium chloride, and silver bromide. Okay, so you can see that this example AgBr was common to both Frenkel and Schottky. Okay, so this is an example of a solid which shows both Frenkel and Schottky defect. Okay, so this is a one marker question. So remember that AgBr can show both Frenkel and Schottky defect. Okay, so now let's have a look at Frenkel and Schottky defect. Yeah, so as you can see in this picture of Frenkel defect, you can see there is a positive charge which is missing here, right? So this cation which was positively charged is found here. Okay, it is found in the interstitial site. Okay, so this is nothing but Frenkel defect. It's also called dislocation defect. Okay, now Schottky, can you see that? So this here there is one negative anion missing, and here there is an anion missing. So two negatively charged ions are missing. So equally, there will be an absence of two positively charged ions. So those two positively charged ions, you can find it here. Okay, so that is nothing but Schottky defect. And this I had already mentioned that AgBr is a solid which shows both Frenkel and Schottky defects. So this question is very important. You can learn the difference between Frenkel and Schottky defect. Okay, it's a 2 marker. So we had learned that point defect can be classified into impurity defect, stoichiometric defect, and non-stoichiometric defect. Okay, so we learned what is stoichiometric defect, and we learned 4 classification of stoichiometric defect, that is Schottky, Frenkel, vacancy, and interstitial defect. Okay, so now we will move on to next type of defect, that is impurity defect. Okay, impurity defect. So the example which we are going to study is NaCl and strontium chloride, sodium chloride and strontium chloride. Okay, so can you see a crystal here? So this is a crystal of NaCl. Okay, so when you are crystallizing molten NaCl which has little amount of strontium chloride, some of the sites of Na plus ions will be occupied by Sr plus 2 ions. Okay, some of the sites of Na plus cation will be occupied by Sr plus 2 ion. Okay, so one Sr plus 2 ion is equal to 2 Na plus ion. Okay, so this is based on charge. Okay, so one Sr plus 2 is equal to 2 Na plus ion. So each Sr plus 2 can replace 2 Na plus ions, and when it replaces 2 Na plus ions, it can sit in place of one Na plus ion, leaving one place of Na plus ion vacant. Okay, so if you see in this crystal, there is one Sr plus 2 ion and one vacant site. So this Sr plus 2 has replaced 2 Na plus ions. Therefore, the number of cationic vacancies produced are equal to number of Sr plus 2 ions. Okay, so since there is one cationic vacancy, there is one Sr plus 2 ion. If there was 2 cationic vacancies, then you will find 2 Sr plus 2 ions in the crystal. Okay, so this type of defect is nothing but impurity defect. Here, strontium chloride is the impurity. Yeah, so we'll just revise it once again. So point defect will be classified into impurity defect, stoichiometric defect and non-stoichiometric defect. So just now we discussed what is impurity defect, and we have discussed what is stoichiometric defect. We discussed all the four types of stoichiometric defect. We discussed what is Schottky, Frenkel, vacancy, and interstitial defect. Okay, so now non-stoichiometric defect. This is the third type of defect, that is non-stoichiometric defect. So in this type of defect, will disturb the stoichiometry of the given crystal. Okay, it disturbs stoichiometry of the given crystal. That is, the number of positive and negative ions may not be in the same ratio. Okay, so it disturbs the stoichiometry of the given crystal. Okay, so now a non-stoichiometric defect can be classified into metal excess defect and metal deficiency defect. Okay, so first we'll learn what is metal excess defect. Okay, metal excess defect can be due to anion vacancies or due to the presence of extra cation. Okay, so let us see what is metal excess defect. So metal excess defect, as I said, it's of two types. Okay, it is due to anionic vacancies and due to extra cation. Okay, so first let us see metal excess defect due to anionic vacancies. Okay, so if this is a crystal of NaCl, okay, this is a crystal of NaCl, and I'm heating this crystal in the presence of sodium vapor. Okay, when I heat this particular crystal in the presence of sodium vapor, so these positive charges are nothing but Na plus ions, negative charges are nothing but Cl minus ions. Okay, and since I told you it is in the presence of Na plus ions, sodium. So when you heat crystals of NaCl in the presence of sodium vapor, okay, so this is one particular crystal. Okay, so these are sodium atoms. So I told you this sodium is there as vapor, right? So these are sodium atoms on top of the crystal. Okay, so when I heat this, what happens is, can you see the Cl minus ions? These negative charges are all Cl minus ions. Okay, so these anions, okay, some of these anions will move to the surface. Okay, so Cl minus, when it's heated in the presence of sodium vapor, will move to the surface. Okay, once it moves to the surface, what happens is it will combine with these sodium atoms. Okay, so sodium atoms which is there on the surface will combine with Cl minus. Okay, so this gives NaCl plus electron. Okay, if this sodium should combine with Cl minus, this Na should become Na plus plus electron, right? This then what happens? This Na plus will combine with this Cl minus to give Na plus. Okay, this electron will be remaining. Okay, so this electron, okay, so when this Na plus and Cl minus combines, you will get NaCl plus one electron. So this electron which is formed will move to the anionic site. So this space was empty now because the Cl minus went out of this anionic site, right? So this vacant anionic site will be occupied by this electron. Okay, this electron will occupy this anionic vacancy. Okay, so this center is known as F centers. Okay, F centers, this anionic vacancy which is being occupied by this anionic vacancy which is occupied by electron is known as F centers. Okay, F is nothing but Farbenzenter. Okay, meaning color. Okay, so because of this electron, okay, this crystal, when you heat NaCl, you get yellow color because you have already learned in your first year, electrons, when they absorb energy, they get excited to a higher state, right? They get excited to a higher state, and when they return back to the lower state, electrons, they get excited to a higher state. Okay, and when they return back to the normal state, they emit energy. Okay, so this color for NaCl will be yellow color. Okay, so when you heat NaCl, you get yellow color. Okay, that is because of the excitation of this electron. So this, in this particular crystal, now when you see in this particular crystal, Na plus is in excess. Okay, so this is metal excess defect due to anionic vacancies. When you count the number of Na plus and Cl minus here, you will see there is shortage in the number of Cl minus ions because they have moved to the surface. Okay, but the number of Na plus in the crystal will be same. These Na which is being combined is from sodium vapors. Okay, it's from sodium vapors. Okay, so that is why this type of defect is known as metal excess defect due to anionic vacancies. This, when crystals of NaCl are heated in the atmosphere of sodium vapor, sodium atoms are deposited on the surface of the crystal. The Cl minus ions diffuse to the surface of the crystal and combine with sodium atoms to give NaCl. This happens by loss of electron. Okay. To form Na plus ions. The released electron diffuse into the crystal and occupy anionic sites. As a result, the crystal now has excess of sodium. The anionic sites occupied by unpaired electrons are called F centers. Okay, this is an important question. Anionic sites occupied by unpaired electrons are called F centers. F is nothing but Farben-Center. Okay, it's nothing but color. Okay, so this center, it imparts color to the crystals of NaCl. Okay, the color results by excitation of these electrons when they absorb energy from visible light falling on the crystal. So if you have lithium chloride, then you can see pink color. If it's potassium chloride, you will see lilac or lilac color. Okay, yeah, so this is the picture. So you can see this is the F center. Okay, you can see there is an anionic vacancy. This was supposed to be a negative ion, right? Instead of that, you have an electron. So this is an F center. So the next type of defect under metal excess defect is metal excess defect due to the presence of extra cations at interstitial site. Okay, at room temperature, if you see, zinc oxide is white in color. So this ZNO at room temperature is white in color. Okay, but when you heat this zinc oxide, okay, it turns yellow. Okay, so when you heat, see the reaction, what is happening? ZNO. Okay, it is giving out oxygen. So this O2 will be gas. So this will escape. Okay, and you will be left with Zn plus 2 ion and electrons. Okay, so these cations, which is these cations will now occupy interstitial site. Okay, so that is why you tell there is excess of zinc. Okay, and the formula will become Zn. It's Zn 1 plus X. So this is that excess of Zn. Okay, 1 plus X. Oh, this will be the formula. So here there's a small correction. This 1 plus X has to be subscript. Okay, so I'll just repeat it once again. So zinc oxide is white in color at room temperature. Okay, but when you heat this zinc oxide, what happens is it will give out oxygen. Okay, oxygen will escape as gas and it will be left with zinc ion and electrons. These zinc ions will occupy interstitial sites. Okay, and even these electrons will occupy some of the sites. Okay, now whatever zinc ions are present, okay, so those will be in excess. Okay, so that is why the formula, instead of ZnO, it becomes Zn 1 plus XO. Okay, so metal deficiency defect is usually seen in FeO. Okay, FeO is nothing but Fe plus 2 and O2 minus. Okay, this should be the composition. So the usual composition of FeO is Fe 0.950. Okay, it can also range from 0.93 to 0.96. Okay, So here what happens is, instead of Fe+2, Fe3 plus ion occupies the space of Fe+2. Okay, so if you see the charge Fe3 plus, okay, 2 ions of Fe3 plus is equal to 3 ions of Fe+2, right? So now here the charge is 6, here the charge is 6. Okay, so 2 ions is equal to 3 ions of Fe+2. So if you have a crystal, okay, and if you have Fe3 plus, so if you have a crystal and if you have 2 Fe3 plus getting into the crystal, then uh, this will remove 3 Fe2 plus from the crystal. Okay, so 2 of these sites will be occupied by these 2 Fe3 plus, but you will have one site of Fe2 plus vacant. Okay, so here the metal is deficient in the crystal. If you see, there will be less number of cations, the metals. So that is why it is called metal deficiency defect. You can just go through what is written for metal deficiency defect. So next, let's move on to electrical properties. Okay, so we are done with defects. We classified point defects into non-stoichiometric defect, stoichiometric defect, and impurity defect. Okay, so you can learn the explanation of defect with example. Okay, so next, electrical properties. So you would have learned these things earlier. What are conductors, insulators, and semiconductors? Okay, so based on conductivity, you can classify solids into these three, that is conductors, insulators, and semiconductors. Okay, conductors are the ones which are the conductivity ranges from 10 power 4 to 10 power 7 per ohm per meter. Okay, insulators are with the substances with very low conductivity. Okay, and semiconductors are substances which has conductivity intermediate to that of conductors and insulators. Okay, let's learn about conduction of electricity in metals. Okay, so how does metals conduct electricity? So electrons are responsible for conductivity in metals, right? So, but if it's a solution, ions are responsible for conductivity. So now we are learning about solids. So here we'll learn about electrons. Okay. So how is this? How are these conductors, insulators, and semiconductors different? Okay, we'll see why conductors are conducting, insulators are non-conducting, and semiconductors are partially conducting. Okay, so for that you need to know what is conduction band and valence band. Okay, a valence band is nothing but the band in which you have your valence electron. Okay, so you might be knowing valence band. It's the outermost shell, right, in which you have your electrons. Okay, so that band will be called valence band. Okay, in which you have your outermost electron. Okay, the next higher level will be called conduction band. Okay, so higher level you have, you can call that as conduction band. I'm writing CB for conduction and VB for valence band. Okay, uh, okay, let's suppose this is your valence band and this is your conduction band. Okay, so the energy gap, the distance between valence band and conduction band, decides whether it's a metal, insulator, or a semiconductor. Okay, now if you see, okay, so in case of metal, this will be your valence band and this will be your conduction band. Okay, so if the valence band and conduction band are overlapping, if it's overlapping, then it's easier for electrons to move from valence band to conduction band and conduct electricity. Okay, but if the energy difference is large, if the energy difference is large between valence band and conduction band, then it's difficult for electrons to move from valence band to conduction band. Okay, so this is in case of insulators. Okay, so look at the diagram. In case of metals, it's partially filled. So in case of metal, as you see, the bands are, it's either partially filled, okay, or you have overlapping band. This is valence band and this is conduction band. Okay, so here it's easier for electrons to move from valence band to conduction band, therefore these are good conductors. Okay, in case of insulators, if you see, there's a large energy difference between valence band and conduction band, therefore it's not possible for electrons to move from valence band to conduction band, therefore these are non-conducting. Okay, now in case of semiconductor, there's a very small energy difference. Okay, so some of the electrons might be able to move from valence band to conduction band. Okay, in this case, in case of semiconductors, if you slightly increase the temperature, more number of electrons will be able to move from valence band to conduction band. Okay, let us study the conduction of electricity in semiconductors. So as I said, the gap between valence band and conduction band is small in case of semiconductors. So because of this, it's easier for electrons to jump from valence band to conduction band. Okay, but if you slightly increase the temperature, there will be increase in the number of electrons going from valence band to conduction band. But so these kind of conductors are known as intrinsic semiconductors. Okay, but this conductivity which you get by increasing the temperature is very low and it's of low practical use. So what you do is you will add an impurity to this semiconductor. Okay, so when you add a particular type of impurity to the semiconductor, the conductivity increases. Okay, and this process of adding impurity to a semiconductor to increase its conductivity is known as doping. Okay, so for doping, you can use two types of impurities. Okay, one is electron rich impurity or electron deficient impurity. So let's learn doping with two different impurities, doping with electron rich and electron deficient impurities. Okay, so the first type of doping is with electron rich impurities. Okay, I just missed the heading. You can just write electron rich impurities. Okay, so silicon and germanium are all semiconductors. Okay, these elements belong to group 14 and they have 4 valence electrons. Okay, so when you dope these elements with group 15 elements, that is arsenic and phosphorus. So group 15 elements will have valence electron 5. So when you dope this with, so when you dope silicon and germanium with group 15 element, you get an N-type semiconductor. Okay. So look at this picture. We have germanium here. Germanium, I told you, it's of group 14 element. So this will have 4 valence electron. So if you see, each of these atoms will have 4 valence electrons. Okay, so it's bonded by a single bond. Okay, now when you add impurity here, phosphorus is the impurity. Phosphorus is from group 15. Okay, so when you add phosphorus as an impurity, phosphorus has 5 electrons. Okay, can you see there are 5 electrons? Okay, so out of these 5 electrons, 4 electrons are getting bonded to germanium. Okay, so here we have 1, 2, 3 and 4. So these 4 electrons are bonded to germanium, whereas we have one electron. Out of this 5, 1 electron is free. Okay, so now this electron can move towards the positive pole and conduct electricity. Okay, so this phosphorus is known as pentavalent impurity because it has 5 valence electrons. Okay, so since a negatively charged particle is moving for the conduction of electricity, we call it N-type semiconductor. Okay, so you can go through the PPT, whatever is written. So when silicon or germanium is doped with a phosphorus or arsenic, when it's doped with phosphorus or arsenic, 4 electrons out of 5 makes a covalent bond, leaving 1 electron free. So this electron is the one which increases the conductivity. And since it's increased because of negatively charged particle, this type of conductivity is known as N-type semiconductor. Okay, so let's learn the next type of doping, that is doping with electron deficient impurities. Okay, so in electron deficient impurities, the impurity which we take will have less number of electrons than silicon or germanium. Okay, so silicon or germanium has 4 valence electron, right? So in electron deficient impurities, we'll use an impurity from group 13, so that it has 3 valence electron. Okay, yeah, so look at the picture. So boron is used as an impurity here. It's of group 13. Okay, so germanium, as we know, uh, germanium, as we know, it has 4 electrons because it's from group 14. Okay, boron, it has only 3 electrons. So these 3 electrons will form bonds with germanium. Okay, so we have 1, 2 and 3. Okay, 3 electrons are forming bond, whereas here you have a hole here. There is no bond. Okay, so since there is a hole here, any electron from the neighbor can jump to this particular hole. Okay, so there's a hole here and electrons can jump to this hole. So when you see, it appears as if these holes are moving in the opposite direction to that of electrons. If electrons are moving in this direction, it appears as if holes are moving in opposite direction. Okay, and it appears as if holes are positively charged. So that is why we call it P type of semiconductor. Okay, and the impurity which we use is a trivalent impurity. It has 3 valence electrons. Look at this picture here. So we have a perfect crystal of silicon atom. So silicon, it has 4 bonds, so it has formed covalent bond. So there is no extra electrons or any empty spaces in this particular crystal. Okay, here you see there is an N-type. This is an N-type semiconductor, where you have an impurity. Arsenic is the impurity. Okay, so you have, since this is from group 15, you have an extra electron here. So this extra electron will be the one which is conducting. Okay, so since this negatively charged electron is conducting electricity, we call it N-type semiconductor. Next, moving on to P-type semiconductor. So boron is the impurity used. So you see here you have a hole here. Okay, so electrons from the neighboring atoms can move to these holes here. Okay, so it appears as if holes are positively charged. They are moving in the opposite direction to that of electron. That is why you call it P-type semiconductor. So that's about doping of semiconductors. Okay, doping is done to increase the conductivity of semiconductors. So we use either electron deficient or electron rich impurities to increase the conductivity. Okay, so you can see the application for N-type and P-type semiconductor. I'll be sending you a PDF of this particular chapter. You can go through the application of N-type and P-type semiconductors. Okay. So the next last topic of this chapter will be magnetic properties. So I'll be uploading that as a separate video.